All right, I'm going to go ahead and try to finish up section 5.2 in this video. So we're on problem 23 in the notes. In the game of roulette, a wheel consists of 38 slots numbered 0, 0, 0, 1, 2, 3, etc., all the way up to 36. The odd numbered slots are red, and the even numbered slots are black. The numbers 0 and 0, 0 are green. Okay, and to play the game, a metal ball is spun around the wheel and is allowed to fall into one of the numbered slots. So in part A, it says determine the probability that the metal ball falls into a green or a red slot. So okay, probability of green or red. Now or is the key word, so I use the addition rule. Okay, so I found the probability of green plus the probability of red. And now, do I have mutually exclusive events going on? Yes, I do, because it's not possible for the ball to land in a green slot and at the same time land into a red slot. Okay, so because that cannot happen, then yes, I have mutually exclusive events. Now, all that means to us is that I'm using the addition rule, but I'm subtracting 0. So there's 38 slots total. 2 of them are green, 0 and 0, 0. And half of them are red. Okay, the odd numbered slots are red. So half of 36 is 18. And so if I take 2 plus 18, I get 20 out of 38, and that reduces down to 10 over 19. Okay, part B, determine the probability that the metal ball falls into does not fall into a green slot. Okay, so the probability of green, but the complement of that means that I don't want the ball to fall into a green slot. So if I use the complement rule, take 1 minus the probability of it landing in a green slot. 1 minus the probability of it landing in a green slot is 2 over 38. 38 over 38 minus 2 over 38 gives me 36 over 38. I reduce that, so I get 18 over 19. Okay, and of course, do I have to do all this writing? No, I don't. Okay, so if I want the ball to not land into a green slot and 2 of them are green, then the other 36 of them are not going to be green, right? 36 divided by 38, reduce that at the end. Okay. Problem 24 says that a standard 52 card deck is shown below. Suppose that one card is randomly selected from the deck. Okay, now before we do this, so sometimes in probability we work with a deck of cards, just quite honestly because they make for good questions. Okay, so I'm going to assume that everyone has played cards before. Okay, now if you've never played cards or never seen a deck of cards before, here's all 52 cards. Okay, they've got a picture of all 52 cards. Whoops. They got a picture of all 52 cards on page 246 in the book, so right here. Okay, when it comes to a deck of cards, I would know the basics. Okay, so know that there's 4 suits. There's the hearts, the diamonds, those are the red suits. The spades and the clubs, those are the black suits. Okay, there's 13 cards in each suit. Now sometimes we have to work with face cards. Jacks, queens, and kings are face cards, and ace is not a face card. Okay, that's pretty much all you need to know. There's 4 2s, 4 3s, 4 4s. Okay, 4 of each kind there. So let's look at part A, where they want us to compute the probability that the card is a 2 or a 3. Okay, so or would be a key word there. Or means add. So the probability of 2 plus the probability of 3. Now, I have mutually exclusive events because if I select one card from the deck, it can't be a 2 and a 3 at the exact same time. Okay, so I would just simply add these 2 probabilities together. 4 over 2 would be the probability of getting a 2. 4 over 2 would be the probability of getting a 3. 4 over 52 plus 4 over 52 is 8 over 52. And 8 over 52 reduces to 2 over 13 is the answer. Part B, compute the probability that the card is a 2 or a 3 or a 4. Okay, so or is a key word. Now this time I've got 3 events. That's okay. I still know that the events are mutually exclusive because I can't select a 2 and a 3 and a 4 at the exact same time. So I'm going to just simply add these 3 numbers together. The probability of getting a 2 is 4 over 52, plus the probability of getting a 3 is also 4 over 52, plus the probability of getting a 4 is also 4 over 52. Add that together, you get 12 over 52, and 12 over 52 reduces down to 3 over 13, which would be the answer. Part C, compute the probability that the card is a 2 or a club. Okay, so 2 or a club, or is a key word, so or means add. Let me use the addition rule. Now this time, I'm going to use the regular addition rule, since a card can be a 2 and at the same time a club. If it's a 2 and a club, it's the 2 of clubs. Okay, so I do not have mutually exclusive events in this one. Okay, because the card can be a 2 and a club. The probability of a 2 is 4 over 52. The probability of a club is 13 over 52. There's 13 clubs in a deck. Minus the probability of getting a 2 and a club. That's a 2 and a club. It's the 2 of clubs. There's only one of those cards out of the 52 cards. So I need to subtract 1 over 52. And that gives me 16 over 52, which reduces to 4 over 13. So 4 over 13 would be the answer there. Part D says to compute the probability that the card is not an ace. Okay, so not an ace means that I want to find the probability of getting an ace, but the complement of that. So I use the complement rule. Take 1 minus the probability of getting an ace. There's 4 aces in a deck out of the 52 cards. So 1 minus 4 over 52 is 48 over 52, or 12 over 13 when you reduce. And of course, make sure that you reduce. If any time the fraction reduces, be sure you give your answer in simplified form. Part E, compute the probability that the card is not a face card. Okay, so the probability of getting a face card but not that means that I want the complement sign there. Use the complement rule. So this is equal to 1 minus the probability of getting a face card. Now there's jacks, queens, and kings are face cards. Okay, so how many face cards would there be total? In the deck, there's 12 cards total that are face cards out of the 52. 1 minus 12 over 52 is 40 over 52, which reduces to 10 over 13. Okay, part F, compute the probability that the card is a spade or a red card. So or is a key word, or again means add. So the probability of getting a spade, there's 13 spades in a deck, okay? Half the deck is red and half of it's black. So there's 26 cards that would be red. And by the way, I've got mutually exclusive events going on because a card can't be a spade and a red card at the same time. So 39 over 52, or 3/4 when you reduce, would be the answer there. Part G, compute the probability that the card is a spade or a face card. Or, again, is a key word that I'm saying there. So probability of getting a spade or a face card means I could use the addition rule. Okay, I got to take the probability of getting a spade plus the probability of getting a face card, and then minus the probability of getting a spade and a face card. Okay, well, 13 cards are spades. 12 cards are face cards. I said that a moment ago. And 3 cards would be spades and face cards. So that'd be the jack of spades, the queen of spades, and the king of spades. When I add these together, okay, 22 over 52 would be my answer, but that reduces down to 11 over 26. Okay, so 11 over 26 would be the answer. Problem 25 says, according to the U.S. Department of Transportation, a total of 34,987 people died in motor vehicle crashes in the U.S. in 2015. The following data represent the number of deaths in motor vehicle crashes in the U.S. in 2015 by age group and by gender. Okay, so I've got a contingency table or a cross-tabulation table. Okay, so the ages are given there, and then the two genders are given. Okay, along with the totals. So part A, I need to determine the probability that a randomly selected individual from this group was male. Okay, so I got to take the number of males, which is 24,837, and then divide that by the total, 34,987. And when I divide, approximately, if I go to the nearest four digits, 0.7099 would be the answer. So there's a 70.99% chance that I would select a person that is a male from this group. Okay. Part B says, determine the probability that a randomly selected individual from this group was a 16 to 19-year-old. Okay, so the probability of selecting a 16 to 19-year-old, there's 3,114 of those people, and the 34,987 total. And so approximately 0.0890 would be the answer to that one. And okay, so part C says, determine the probability that a randomly selected individual from this group was a 16 to 19-year-old male. Well, so they have to have both these items together. So the male and 16 to 19 years old. Okay, and look at my table here. So 16 to 19 years old, a male. So there's 2,099 of those people, and out of the 34,987 total, and 0.0600 roughly, or a 6% chance would be roughly what I get as the probability of selecting a person that is a male and 16, 19 years old. Part D says, determine the probability that a randomly selected individual from this group was male or 16, 19 years old. Okay, or would be a key word, and or means add. So I could use the addition rule. Okay, let's take the probability of getting a male plus the probability of getting a 16 and 19-year-old. And then, now, do I have mutually exclusive events for this one? No, I don't, because a person can be male and 16 and 19 years old, right? There's 2,099 of those people. So I need to make sure I'm using the regular addition rule and subtracting here. Okay, now I've got the decimals given, and so I'm using the decimals next. The probability of getting a male will be 0.7099 plus the probability of the individual being 16, 19 years old is 0.0890 minus the probability of the person being male and 16, 19 years old is 0.0600. Okay, so when I simplify that, 0.7389 would be my answer. Okay. Part E says, would it be unusual for a randomly selected individual from this group to be a 16 to 19-year-old female? Why or why not? So I need to find the probability of the person being female and 16, 19 years old. Okay, so if I go to my table here, so here's 16, 19 years old and female. There's 1,015 of those people out of the 34,987 total. And when I divide, I get roughly 0.0290. Okay, so would that be unusual then if I were to select a female and that person is 16, 19 years old? Yeah, it would be very unusual. So I only have a 2.9% chance of that happening. Okay, so it's likely not to happen. It could happen, right? We're not saying that it can't happen. It's just it's likely not to happen since you have less than a 3% chance of that happening. Okay, so yeah, that'd be kind of unusual then for that to happen. Okay, so I'm done with section 5.2. Here's the homework that you want to look at when you get a chance, and we'll go ahead and stop the video right there.